So for this session, we have two talks. For the first talk, I'd like to welcome Mylov from Roseman Labs to talk about progress and cancellation, managing ongoing computations in an MPC application server.
Thank you. So my name is Mylov Veningen. Very happy to be here and to be talking about some of the practical work that we've been doing on multi-party computation. So I work at Roseman Labs. So this is the real-world multi-party computation workshop, and I think we like to really think of ourselves as a real-world MPC company. So we started kind of 5 years ago. Actually, we had our Jubilee party last week. And nowadays we're a company of like 34 people. And we're doing real-world MPC in the sense that we have a product. It's actually being used on a kind of daily basis by various customers in areas like healthcare, government, and consultancy. And so when building a real-world MPC product, I think there's some real-world challenges. And it's nice that in a workshop like this, there's a chance to be talking about them. So sort of if you think about what it means to build a multi-party computation application, I think you can look at it at several levels, say. There are several layers in which you need to do work. There's the application layer that will be talked about later today. There's various protocols layers at various levels of detail. We discussed that this morning. There's also the system design. And I don't think that gets talked about a lot in practice in events like this. So that's why I decided to take up the challenge to see if I could say something interesting about the system level design of an application that uses multi-party computation. And that's what I'll be talking about today, and I'll be talking about our own MPC framework. So just to talk about that a little bit, so what is actually our product? So our product is the Roseman Labs engine. So basically what it is, it's MPC core. It's really simple. It's just Shamir secret sharing on its majority passively secure, doing multi-party computation. And for the purposes of system design, I think there's two things that are relevant today. It's monolithic and it's what I call dynamic. And I will talk about what these two things mean. So that's our application engine. How do you interact with that application engine? Several ways. One of them is using kind of a simple API. And what is important to know in this setting, so basically one of the API we have is a Python package. And you can use that Python package to kind of interactively talk with our MPC engine. So you can upload data, you can run computations on them, and then you can download in the end the results. And the kind of computations on them, there are simple, basic tabular operations at their core. So you have a table, you compute a new row or a new column of the table, you join tables, you concatenate them, you filter them, those sort of things, and then you can do more complicated stuff like statistics, machine learning. So sort of the way in which you interact with this engine is kind of in a dynamic way by doing these small queries. So what I mean by monolithic, I mean that our application engine is basically just one, at the system level design, it's just one executable that is running at the different engine nodes. So that application is running potentially many of these operations at the same time. And it's dynamic in the sense that, well, the thing that you do is not kind of a fixed computation that is completely fixed in terms of having a binary circuit or something, but it's actually dynamic. So if you join two tables together, what exactly is going to happen will depend on what those tables actually are, so on the metadata of stuff that is already in the server, for instance. So it's monolithic, it's one application, it's doing several things at the same time, and it's dynamic in the sense that it determines what to do kind of dynamically based on the data that it sees. And how do we then do that? Kind of at a very, very high level system design. Kind of the way in which you can do this is by using the async await paradigm. It's a paradigm that is available in many programming languages today, and that you can use to implement this kind of monolithic concurrent style of programming. So basically, because we're dynamic, we cannot kind of compile a circuit and then just run it. We need to kind of directly implement the MPC protocol and run it line by line. By using this async await, you can deal with this problem doing many things at the same time and allocating resources to that. So basically what I see here is I'm gonna, if I can get this to work. I'm going to do 2 invocations of a signed computation, so doing a multi-party computation comparison. And by doing this kind of gather operation, I can do both at the same time. So it enables me to do concurrency at a smaller level, but also at a higher level of doing multiple operations at the same time, with multiple high-level operations, such as multiple table joins and that sort of thing. And then in the end, MPC is going to involve communication, right? And also for that, this async await is useful because when I have an operation like reveal, which is going to open results to parties, that's going to involve computation. I have to wait, or that's going to involve communication between the parties, and have to wait until the communication actually happens. I send some message, I have to wait for the result. And basically, this await statement here allows me to suspend kind of this piece of running code. I suspend it until the result of that operation arrives from the other parties. And then, while this is going on, any of the other operations can keep on running. So that is the async await, and that is what happens kind of at one of the engine nodes. So that enables us to do many things at the same time, in a concurrent way and in a dynamic way, depending on the data that we see. So that is the basic idea, but then of course that poses the question, if I have several of these engine nodes, they need to talk to each other. And if these, for instance, these signed protocols, they happen at the same time, and it's not kind of a well-defined order of messages. So how do I actually identify these different messages that come from these different protocols? So for that, there's a very old idea that has already been used, for instance, in MPC or even VIF, like the very, very old multi-party computation frameworks. And that is to use a program counter. And there the idea is that even though the operations happen in a kind of undefined way, I keep track of a program counter that provides me a well-defined kind of order of messages. So basically the high-level idea is that at the highest level, I just increment my program counter, and when I enter a subroutine, I'm going to fork it by computing a hash of that program counter, and in that subroutine, I work on that hash. Right, so that enables me to kind of keep track of a unique message identifier that is consistent between the different parties, and that is independent from the order in which messages are sent if many things happen concurrently at the same time. So that at a very high level is kind of how you can code such a monolithic kind of engine that can do many, many things at the same time, while allowing the interaction that you need for multi-party computation. So if we go back to our MPC product, really that's then how it works. So basically we have a HTTP endpoint. You submit a query to it that kind of triggers a fork of the main program counter. Within that fork, kind of the computation, whether it's a join or a concatenation or whatever, that happens in the context of that fork's program counter. And yeah, that computation keeps on running, and that in the end provides a response that's being sent to the client. And initially, this is really how our application works. So we had an HTTP endpoint. You submit a query, computation happens, and through a result, through a response to that HTTP query, you just send back the computation result in some kind of masked way. And that worked quite well for a while. People were able to experiment with this, but as we got more customers and they got to actually use the product, it turned out that this wasn't really enough. And kind of the motivation why it's not enough is maybe best demonstrated by a movie, which I'm not sure is going to play. Let's see. So the point is, this is an example here. I'm making a table which is pretty big. It has 1 million rows, and I'm going to do a group by operations on that table. So let's see if I can get that operation to run. I cannot. Do you know how I can show the video of the previous slide? Can I go back to the previous? There's a video. This is a PDF, I think.
Yeah, this is a video.
Okay. What is going to happen in this video is I'm going to do I'm sorry I cannot show it to you. It's a beautiful thing. No problem. But of course, the point is, as we all know, multi-party computation is not instantaneous. I run a computation, I do it on 1 million rows, and it's not going to directly give me the result, right? It's going to run, and it's going to run, and it's going to run. At some point, the user is going to think, what is going on here? The user wants to know that actually the computation is still running, wants to have some idea of when the computation is ever going to finish, right? So we need to have some way of providing the user with some progress of the ongoing computation. User wants to know how far the computation is. And if the user sees, well, this operation is still going to take 3 hours, doesn't want to wait, we need some way to actually stop that ongoing computation. And we should do that in such a way that not only is the client not waiting for it anymore, we actually want to stop it at the server. Because if the user starts 10 of these joins, no longer interested in, we don't want to actually compute them. So we need some way of dealing with these ongoing computations that are happening. So in terms of our API and our system level design means we do not just deal with the situation that a query gets submitted and a response gets provided. We need to be able to push progress updates from the server back to the client, and we need some way of canceling queries. So those are kind of two very practical problems that when you try to ship this stuff to customers and they're working with it, that's something that you really, really need. And how can you now do this? So that's what I want to talk about today. So first I'll talk a bit about progress updates, and then let's see if I have time to discuss cancellation. So progress updates. So if you think about it from a very high level, I think there's two kind of main approaches you could take at implementing progress reporting for a given program that you have. You could sort of consider a white box approach, where basically you just manually add these progress callbacks to your existing program. So you take a program, and if you have a loop, which ranges over a number of rows, you just execute your MPC operation, and then you just compute, okay, I did row 10 out of 100. It means I'm at 10%. I'm just going to send that to some progress reporting facility. So we approach number one. And approach two would be kind of a black box approach, where I try to avoid having to manually annotate every single line of my, or single loop of my program. Instead, what I want to do is I want to treat my program as a kind of black box that just receives some input and output, but that I don't know the internals of. And somehow I want to extract some information from that box that allows me to estimate how far I actually am. Now, both approaches, of course, have some pros and cons. Mainly, the first approach, as you can imagine, it's a lot of work. And also, most MPC operations that you do are not as simple as this. It's not a simple loop where you can just say, I'm now at 30% because I processed 30% of the rows. So even an operation like filtering, where you take a subset of rows that consists of a permutation, that consists of evaluating the filter criterion, that consists of applying this permutation. So even such a thing like that is not simply a loop. And really the only, if you have several of these operations running, to know which one's taking how much time, really the only way to do that is by measuring. So it's not so easy, especially not if you have like 30 or 40 operations as we have. So that's something you don't want to really do. So how about the black box approach? I think there you have the problem that many of the obvious metrics that you can imagine, such as the amount of communication that has been done, the amount of time that has been spent, even the rounds, number of rounds that you've performed so far, all of them depend on the data that you're operating on. So if you have a join, the number of rows of the join and the number of columns, that affects all of these different metrics. So you can measure these things, but it's not so easy to derive a percentage from those metrics. So what do? Well, luckily there's a way out, and that way out is because all of these things vary per operation, but there's actually one thing that, per instance of an operation, but there's actually one thing that doesn't vary, because it has been specifically designed to be the same and to be consistent over different executions of the same algorithm. And that is the program counter that I've been talking about. So kind of the observation, we have our existing implementation of an MPC protocol. It's going to call this fork function to fork a program counter throughout the execution of the protocol many, many times. And every time that happens, we get a program counter which tells us actually, or which depends in a kind of predictable way on where we are in the operation. So this program counter evolves mostly in the same way for each instance of an operation. And the idea would be to see if we can use this actually to derive these progress updates. And again, this example that I showed before shows that we have a program counter and it evolves in a kind of predictable way because at the main level it increases and kind of at sub-levels we take the hash. So it evolves for different instances of the same protocol, even if I'm running them at the same time, evolves in the same way. However, it doesn't start from the same value, of course, because if I have several instances of a joint protocol, they each have their own starting program counter, otherwise we cannot distinguish them from each other. So that is, but still it evolves in the same way. So then the way that you can fix this to make this useful for progress updates is actually very simple. Kind of you just split the program counter into two parts, one which identifies which instance of the protocol you're in, and one which within that instance defines where we are in that instance. So basically in that instance I just start at 0 and I work from there. That means that different instances of the same filtering protocol, for instance, start from the same program or have the same starting in instance counter and then evolve in kind of the same way. And the way that this then works is simply that we do not change the implementation of the protocol, not at all. We're just changing what the fork function does, because it's just going to call a progress reporting function over there. It's going to give it this in-instance counter. And basically what it's just going to do in the most simple form is just look that up in a table. The table says, if I have program counter number 1, I'm apparently at 87% of my computation. And that's just what I'm reporting back to the client. And then the way in which I derive this table would be by doing a calibration, right? So I just perform the application, or I just run all my operations sometimes on some example data. The data doesn't need to be very representative of the data that I'm actually going to use, but it has to be somewhat representative. I'm just measuring for that example. For instance, at program counter 1, I had communicated 1 megabyte. Overall, I had communicated 1.2 megabyte. That means that I'm at 87%. So that's kind of the basic idea. And that sounds very simple. And it is. So does it actually work? Well, yes and no. So actually, if you try to do this, you implement it just like this, just as I showed on the previous slide. Actually, it works surprisingly well. For many operations, it will give you kind of meaningful progress updates. I think several reasons for this. One of them is that in MPC, we try to avoid stuff that depends too much on the data. So many things like if statements, you don't find them too much in MPC applications anyway, which is useful for having this consistent evolution of the program counter. And also because of this kind of forking level design, if I have, for instance, my filter, which has 4 steps, that is the high level structure. Then whatever happens after a fork doesn't matter for the high level program counting. So as long as the high level protocol follows these 4 steps, that means that at least for those 4 steps, I get meaningful progress updates. And then somewhere further down the evolution of the program counter, in a fork of a fork of a fork, there may be something that depends on data, but that doesn't really matter for the overall progress updates. So you will find, if you try this, that an initial implementation already works quite well. Not quite well enough to give meaningful progress updates for everything. So there's always some manual work still to be done. If there are if statements that are used, so if I use different variants of an operation, I need to do some rewriting to make sure that if I enter such an if statement, I should do a fork of the program counter before the if statement and not inside the if statement. Otherwise, the whole rest of the program will not have the same evolution of the program counter anymore. I need to do something with loops. Loops are a problem because there's really no way from this black box to see how many times it's going to execute a loop unless I know it. That means that for the progress reporting facility, there's no way of getting around the fact that we just need to tell the progress reporting facility how many loops there is going to be done in total. So for that, we need to do some kind of manual annotation. But other than that, it's pretty much just implementing this hook that we attach to this program counter. Some more kind of variants that some things to think about. Joins have different variants. I need to make sure I calibrate all of them and that the program counters of those different variations of the operation do not get mixed up. But there's ways of doing that. And for some stuff, like doing stuff that is performed at multiple cores or that's performed in a factorized way, I need to do some thinking to make that work. But at a high level, this is the design that we have. That's progress reporting. So I promised to also say a few words about cancellation. So cancellation means that if I have a running operation, I want to cancel it. Cancellation can happen for various reasons. It can be because the user wants to cancel it. It can also be because there has been an error at one of the application nodes, has run out of memory or disk or whatever. If the other nodes don't know that, they will continue waiting for a message of that one node. So actually, when there's an error at one of the nodes, we need to propagate that to the other nodes, and they have to report it in the end to the client. It can also be that there's just a stall detected for some reason or another. The protocol is not progressing anymore. That also happens in practice. So for that, we need to have cancellation. We need to be able to cancel a running MPC implementation. For that, you can also use this sort of black box approach. There, the idea is we have our MPC black box. We put it in a white box. The white box is kind of the monitor. And the approach is then simply to wrap our MPC algorithm, to check once in a while whether it needs to be cancelled, whether a request by the client to cancel it or something or another trigger has been received. If that happens, we simply cut off the communication. Whenever the MPC algorithm it's running, at some point it needs to communicate. It's an MPC application, so it will communicate. At that point, we just cut off the communication, and the monitor just stops providing data and instead gives an error. So basically, also that allows us to have just a running MPC algorithm. Basically, if we, by just on the outside of it, dealing it like a black box and manipulating it, we can cancel it. So here there's actually some technical details that make this kind of difficult to implement. There's a lot of things that you need to think about to make this work well that you wouldn't directly consider. But I don't want to talk about that today. Just know that kind of at a high level, such a black box design can also work for cancellation. So that's what I wanted to highlight. So what I wanted to say at a high level, and I'm showing these progress bars, progress and cancellation as an example, is that implementing MPC, it has implications at the system level. It's not just implement or thinking about protocols. It also means thinking about system level design, and that system level design is often impacted by the fact that we use multi-party computation, the fact that it's an interactive protocol between different parties that has a lot of effects. For progress estimation, I've shown you that it becomes important because we're using MPC. Things are slow. We need to basically provide progress updates for everything because everything can potentially take more than a few seconds. But the fact that we use MPC, that we communicate with the outside world, that we do this in a kind of fixed pattern, actually makes it easier to implement progress reporting. And similarly for cancellation, also here we can use such a black box approach. It is hard to get right, but it can be done. And I hope, by this I've shown that also at the system level there are it's useful to talk about the design of MPC application. That's what I wanted to talk about. Finally, I can show you one progress bar. That's the progress bar of this presentation. That's done. Thank you.
Thank you, Mylon, for that great talk. I think this is a great example of a real-world challenge that you're not going to see in kind of an MPC paper, but something that is obviously difficult to solve. I had one quick question. You mentioned kind of white or black box approaches. I was wondering did you consider maybe like a gray box approach where I'm imagining there might be some of your operations that are more expensive than others, and you can kind of do this kind of hybrid approach with only modeling those expensive ones. Step away from the speakers. Sorry about that.
Good question. Yeah. Basically, what we did is a kind of gray boxing approach in a way, right? Because for loops, we have to annotate the number of times we're going to execute the loop. So we are changing some way the program. But it's nice that for many operations, like if we have 30 operations in our server, we maybe need to change 5 or 10 of them, or some of the main places where the progress reporting goes wrong. But for many operations, we don't need to change anything. So that's kind of
Cool.
Yeah.
Thanks. Carrying the program counter along with your whole code, how expensive is that for you?
You mean in terms of implementation
Runtime.
costs?
Yeah, no, runtime costs. I mean, it depends on what's your. The examples you showed were rather simple, let's say. But if you're running like full matrix operations, all of these operations, that whenever you do something, if you're carrying a program counter along and incrementing it, it is an overhead. It's like you have to look up it. You can look it up in memory and so on and so on. So we have to make sure it's always there. It creates like architectural considerations for you. For example, in ShareMind, when we've done our virtual machine, we threw out almost everything in there, because simple loops can cost you so much if you're not building like a proper thing. So have you measured how much you lose by carrying that?
I think what is important in our design is we do almost everything in a factorized way. So whenever we do things on individual elements or factors, we do not carry program counter for individual elements, right? So as soon as you...
Yes, we do the same.
Yeah.
But the point is, when at some point you have to put those vectors together in some loops, for example.
I think we didn't really measure it because we have our kind of build system, which does some test suite and everything, right? I don't think it had a measurable impact on the execution time for that test suite. So I think we never really looked at that much further.
So at some point when we started doing like big stuff, then if some people managed to build these like ON triple, ON to the third kind of loops, and then this overhead starts hurting you somewhere. If anyone uses your tool to implement something like that, then the program counter counting will be an important part of your runtime.
Yeah, that's a good point. Maybe.
Hi, follow up just to get the terminology right for myself. So the program counter, like the program would be one invocation from the client side, I assume. Like calling from the client side from this Grandas library.
Well, basically what happens is we start our whole MPC engine. The whole engine starts with one program counter, and basically everything forks from that. So when you have a new filter coming in, that's a fork from the original program counter.
Okay.
Actually, when we enter a loop, because kind of loops you have to enter in a special way, that's another sub-program that gets a special sub-program.
Okay, and then fork, this was going to be like the next question. Fork is just like calling a subroutine, like a sub-protocol, or if you just like, okay, then I understand.
Actually, any sub-function basically, or anything that happens can happen at the same time.
Okay, thanks.
I think we have time for one more question.
Thank you for your nice talk. I think it's very important to get the system design like in place. Have you considered adding a compilation step beforehand? Would it help you to get like a more granular view of the instructions that you're about to execute in the runtime? And how much would it cost?
You mean a more like compiler approach?
Exactly, yeah.
No, we've not. Kind of our basic design has always been to kind of do things in a dynamic way. We're not using any. But maybe Nick can. You want to comment on that?
Yeah. So, in some sense, we use a compiler because we use a compiled language to implement the engine. But that's not the type of compiler that you mean. You mean the circuit or the protocol compiler. What we have seen in frameworks that have these compilers, then you see that these compilers are immature. So if you want to do very large things, then the compiler goes out of memory, and then what? Whereas we do like straightforward optimizations by hand. For example, if you think about changing the order of doing a resharing and a bunch of multiplication, say if you want to do an efficient inner product, then we do that by hand, or we have a convenience function for that. We usually see that to get the good performance, you need to make sure that you get fast to the network card and back and do compute on large columns of data with like, I don't know, SIMD or have the compiler vectorize your code. So there, I guess we win by relying on the C++ compiler rather than maybe do more clever tricks. But I think if we would have a much bigger team, then we could do that. But it's, I think, the trade-off between working with a resource constrained team as a beginning company, and then we made that decision to be able also to handle very complex type of protocols that you just now execute on the fly, rather than that some kind of compiler written in Python goes out of memory or stops, and then you're blocked.
Let's thank our speaker one more time, please.